A galaxy exists at the edge of time. Its light has been traveling toward us for 13.4 billion years. When it left, the universe was 290 million years old, and it already contained oxygen, which the laws of physics said was impossible. Scientists named one survey after it, Mirage or Miracle. An astronomer at the University of Kansas lay awake at 3 in the morning wondering if everything she had ever done was wrong. A Nobel laureate told the world that what his telescope found meant, quote, "We have misunderstood the universe. If you find any of this as disturbing as we do, stay with us. Like and subscribe, because this story is nowhere near over. Let's begin." Picture the farthest thing you can imagine. A star so distant its light left before Earth existed. A galaxy so remote it sits at the very edge of the observable universe. Now imagine finding one that should not be there at all. That is exactly what happened, and it changes everything we thought we knew about how the cosmos was born. December 25th, 2021, Christmas morning. Across the planet, children were tearing open wrapping paper. Families were gathering around tables, and somewhere in the middle of all that ordinary joy, a rocket sat on a launch pad carved out of the jungle in French Guiana on the northeastern coast of South America. Inside its nose cone was something that had taken 30 years to build, had cost $10 billion, and had broken the hearts of everyone who worked on it at least once. The rocket was an Ariane 5. The payload was the James Webb Space Telescope. 7:32 in the morning, local time. The countdown reached 0, and the rocket climbed. There were no crowds cheering in the street for this launch. The people who understood what was at stake were too terrified to cheer. In control rooms in Baltimore and Paris, and across Europe, engineers sat with their hands folded, their eyes fixed on screens, barely breathing. They had spent years running through every possible scenario of failure, every bolt that could shear, every motor that could jam, every circuit that could arc and go dark. They had counted them, 344 single points of failure during deployment alone. 344 moments where a single mechanical mistake, a single stubborn latch would end the mission permanently. There would be no shuttle to fly up and fix it. There would be no second chance. The telescope was too far away, and it was heading farther still. The original plan called for a launch in 2013. Then the mirrors were redesigned, then the sun shield was redesigned, then the budget doubled, and doubled again. Scientists who had devoted their careers to this machine watched deadline after deadline slide past. Some of them retired before it launched. One of the telescope's earliest champions, John Mather, a Nobel laureate who had been working toward this moment since the 1980s, stood and watched the Ariane 5 rise into the morning sky above the jungle. He did not celebrate yet. Nobody did. The James Webb Space Telescope was the successor to Hubble, but calling it a successor undersells how different it is. Hubble sees primarily invisible light, the kind human eyes can detect. Webb was designed to see something older, something dimmer, something that Hubble could never reach. It was designed to see the first light ever released in the universe. Light so ancient and so faint that it had spent the entire history of the cosmos traveling toward us. To do that, it needed to go somewhere cold and still, far from the warmth and glare of Earth. The destination was a gravitational sweet spot called Lagrange Point 2, approximately 932,000 miles from Earth, on the side opposite our star. Out there, a spacecraft can orbit in relative stability, kept in place by the combined gravitational pull of the Earth and the star it orbits. It is a place of extraordinary stillness, and that stillness is exactly what the telescope required. 14 minutes after launch, the solar panels deployed, power flowed, the telescope was alive, but the engineers knew that being alive and being operational were two very different things. Ahead of them lay the most complex and dangerous sequence of maneuvers ever attempted in the history of space exploration. And it had only just begun. Consider what was riding on this. Astronomers at universities in dozens of countries had structured entire research programs around data that Webb had not yet collected. Graduate students had chosen dissertation topics. The Hubble Space Telescope had famously launched with a flawed mirror in 1990, but astronauts flew up and repaired it. Webb had no such safety net. Whatever was going to unfold over the next 29 days was final. There was no repair, no patch, no second mission. The rocket was gone. The telescope was alone, and the distance between it and any helping hand was growing by miles each second. To understand what the James Webb Space Telescope can do, you have to understand what it is made of and why every single design choice was forced on the engineers by the laws of physics themselves. Start with the mirror, 6.5 meters across, roughly the width of a large living room. 18 individual hexagonal segments, each one shaped from beryllium, a metal chosen because it is both lightweight and extraordinarily stable in extreme cold. Each segment was then coated in gold, a microscopically thin layer chosen because gold reflects infrared light better than almost any other material. Assembled together, those 18 segments form one of the most precise optical surfaces ever manufactured by human hands. The tolerances involved would be invisible to the naked eye even under bright light. But here is the problem. A mirror 6.5 meters wide cannot fit inside a rocket fairing. Rockets have a fixed diameter, and the mirror is simply too large. So the engineers designed the mirror to fold. 18 segments arranged into a central core and 2 side panels that hinge inward like a set of wings tucking against a bird's body. The whole structure collapses into a shape compact enough to fit inside the Ariane 5 and then unfolds in space after launch. Nothing like this had ever been attempted at this scale. The sunshield posed a different kind of engineering problem. To see in infrared, a telescope must be extraordinarily cold. Any warmth, including the warmth radiating from the telescope's own structure, would contaminate the signal. The instruments needed to operate at negative 447 degrees Fahrenheit, a temperature close to absolute zero, colder than the frozen vacuum between most stars. To achieve that, the telescope needed to be shielded from every possible heat source. Our star, Earth's reflected light, even the warmth of the moon. The solution was a 5-layer thermal barrier, roughly 69.5 feet long and 46.5 feet wide, made of a material called kapton, each layer aluminized to reflect heat. Think of it as the world's most sophisticated space blanket, the size of a tennis court and as thin as a human hair. On the star-facing side, the shield absorbs enormous heat. On the telescope side, the temperature drops to nearly nothing. That gradient, across just a few feet of layered film, spans hundreds of degrees. Even that was not cold enough for one of the telescope's 4 instruments. The mid-infrared instrument, which observes the longest wavelengths and therefore the oldest, most redshifted light in the universe, required active cooling, a refrigerator system built into the spacecraft to push its detectors down to operating temperature. It is one of the most sophisticated cryogenic systems ever sent to space. All of this was designed for one purpose: to capture infrared light, ancient light. When the universe was young and the first galaxies were forming, they released light at visible and ultraviolet wavelengths. But in the 13+ billion years since then, the universe has been expanding. Space itself has stretched, and as it stretched, it pulled those light waves with it, elongating them from visible wavelengths into the infrared spectrum. By the time that ancient light reaches us, it is invisible to human eyes. Every camera on Earth, every optical telescope ever built, cannot see it. Webb can, because Webb was built specifically to receive it. That is what was folded inside that rocket on Christmas morning: a time machine, a light collector designed to receive messages sent before the Earth existed, messages stretched and dimmed by 13 billion years of travel. There is something personal about this, even if it does not feel that way at first. Every atom of oxygen in your lungs, every atom of iron in your blood was forged inside a star that lived and died before our solar system formed. The James Webb Space Telescope was built at the deepest level to answer questions about where all of that came from. The question was whether the messages it would decode would confirm what scientists already believed about the universe, or say something far more unsettling. Before the James Webb Space Telescope ever turned its golden mirror toward the sky, cosmologists believed they understood, in broad and confident terms, how the universe worked. That confidence was not arrogance. It was earned, built piece by painstaking piece, over decades of observation, calculation, and experimental confirmation. The model they had assembled was called Lambda Cold Dark Matter, and it was one of the most successful scientific frameworks ever constructed. Here is what it says. The universe is made of 3 components, none of which are evenly matched. Only 5% of everything that exists is ordinary matter. Atoms, molecules, the stuff that makes up stars and planets and oceans and you. 27% is something called cold dark matter, invisible to light, detectable only through its gravitational effects on the galaxies it surrounds. The remaining 68% is even stranger, a property of space itself called dark energy, which drives the accelerating expansion of the universe. Together, these 3 ingredients, in those precise proportions, reproduce almost everything astronomers can observe. The model also described how structure formed. In the earliest moments after the Big Bang, the universe was a near-uniform fog of hydrogen and helium, with tiny fluctuations in density scattered throughout. Gravity pulled at those fluctuations. Dense regions attracted more matter. Over hundreds of millions of years, the fog collapsed into the first stars, and those stars gathered into the first dwarf galaxies, and those dwarf galaxies slowly merged and accumulated into larger ones. Small first, large later. That process, called hierarchical structure formation, was one of the model's most fundamental and most tested predictions. Heavy elements were a key part of that story too. The early universe contained essentially no oxygen, no carbon, no iron, no silicon. Those elements did not exist until the first generation of stars forged them in nuclear furnaces and then scattered them across space in violent supernova explosions. After those explosions, a new generation of stars could form, incorporating the debris of the first. Then those stars died too, and a third generation formed, richer still, each generation leaving the universe more chemically complex than it found it. Astronomers calculated that building up a meaningful quantity of oxygen, enough to detect spectroscopically in a distant galaxy, required at least 1 billion years of stellar birth, death, and recycling. For decades, every observation pointed the same direction. The Hubble Space Telescope peered into deep space and found exactly what Lambda Cold Dark Matter predicted. The farther back you looked, the smaller and less developed the galaxies appeared. The universe had assembled itself gradually, the way a city grows from scattered settlements into a metropolis. It was ordered, it was elegant, it was consistent. Cosmologists had won. The universe had confessed its structure, and the confession matched the theory so well that many scientists began to wonder whether the great questions of cosmology might actually be answered within their lifetimes. They were right that the answers were coming, but the answers were not the ones they expected. Understand what was at stake in that confidence. Lambda Cold Dark Matter was far more than a theory in a textbook. It was the organizing principle behind billions of dollars of telescope time, behind every major cosmological survey of the previous 2 decades, behind the careers of hundreds of researchers worldwide. If it was seriously wrong, entire research programs would need to be reconsidered. Textbooks would need rewriting. The coherent story of the universe that science had spent 50 years assembling would develop cracks that nobody knew how to fill. The Standard Model was the foundation on which modern cosmology stood, and Webb, still months from its first science images, was about to step on it. 29 days, That was how long it took for the James Webb Space Telescope to either become the most powerful observatory in human history or become the most expensive piece of debris ever sent into deep space. The deployment sequence began almost immediately after launch. There was no time to celebrate the successful liftoff, no pause to let the tension break. The telescope needed to transform from a folded package inside a rocket fairing into a fully extended observatory, and it needed to do it without any human hands to help. Every step had to happen automatically, driven by pre-programmed commands, at distances too great for any real-time correction. If something went wrong, the team on the ground could watch it happen and do essentially nothing. First came the solar array, deployed within minutes of separation from the rocket. Then the high-gain antenna, which the mission needed to communicate at full bandwidth. Those early deployments went cleanly. The engineers exhaled, just slightly. Then came the sun shield, that enormous gossamer structure folded into a compact stack for launch, had to be pulled out, tensioned, and separated into its 5 distinct layers, each one stretched taut across a frame the size of a tennis court. The operation involved hundreds of individual mechanical steps, motors reeling in cables, booms extending, membranes pulling flat. Any snag, any tangle, any motor that drew too much current or too little could crumple the shield into useless wreckage. For 5 days, the team watched the shield deploy one agonizing increment at a time. It worked. The layers separated, the shield tensioned. The cold side of the telescope began to cool. Next came the secondary mirror, which needed to swing out from its folded position on 3 spindly support struts and lock into precise alignment. Then the 2 side panels of the primary mirror had to hinge outward from their folded position. Each hinge had to rotate to the exact correct angle and then lock permanently, because there was no mechanism to rehinge them if they stopped short. The panel deployments happened over 2 consecutive days in early January 2022. Controllers in Baltimore called out each latch as it engaged. A room that had been holding its collective breath for nearly 2 weeks finally allowed itself a few tears. But the telescope was still not operational. 18 mirror segments, now extended, were each slightly misaligned. Each one had to be individually adjusted using small actuators on the back of every segment, nudged by fractions of a millionth of an inch until the 18 separate reflections of a distant star collapsed into one sharp, unified image. That alignment process took weeks. Engineers observed a bright star called HD 84406 and watched as the 18 ghost images slowly, painstakingly converged. March 11, 2022. The final alignment check came back clean. 18 segments were one mirror, one perfect mirror, colder than almost anything in the natural universe. Parked nearly 1 million miles from home, pointed at the oldest light in existence. The telescope was ready. The universe had no idea what was coming. Think about what that alignment process actually represented. 18 mirror segments had been manufactured in different facilities, shipped across the country, folded into a rocket, vibrated by the violence of ascent, and then set adrift nearly 1 million miles from any tool or technician. Through weeks of careful remote adjustment, those 18 separate pieces of gold-coated metal became a single, flawless reflector. The precision was comparable to adjusting a mirror until it could detect the heat of a candle flame from the distance between Washington, D.C. and Los Angeles. That is the instrument that now waited, still and cold, aimed at the oldest darkness in existence. July 12, 2022. The White House hosted an event. The President of the United States stood before a screen and unveiled the first official science image from the James Webb Space Telescope to the world. What the world saw stopped people in their tracks. A field of thousands of galaxies, each one a different color, each one a different shape, spirals and ellipses and distorted smears, covering a patch of sky so small that if you held a grain of sand at arm's length, it would cover that entire region. Every point of light in the image was not a star. Every point of light was a galaxy, containing hundreds of billions of stars. The image reached farther back in time than any photograph in history. Scientists and journalists and members of the public stared at it and felt something that is hard to describe. Awe is probably the right word. A kind of vertigo that comes from suddenly understanding, viscerally rather than intellectually, how vast and ancient the universe really is. The celebration was genuine and widespread, but in research offices at universities across the country and around the world, some astronomers were looking at those early images with a growing sense of unease. Among them was Garth Illingworth, an astronomer at the University of California, Santa Cruz, who had been studying distant galaxies for decades, and who knew better than most what those galaxies were supposed to look like. The earliest galaxies, according to every model, should look small, disorganized, faint. The universe at that age simply had not had enough time to build anything bigger. What Illingworth and others were seeing in the Webb data did not look like that. Some of those objects looked unexpectedly large, unexpectedly bright. One word kept coming up in private conversations among researchers: wrong. Richard Ellis, a cosmologist at University College London and one of the most respected observational astronomers alive, was among the first to say it publicly. Looking at the early data, he told colleagues, "It worries me slightly that we find these monsters in the first few images." Monsters. It was not hyperbole. These galaxies, if confirmed, were too massive to have formed in the time available to them. They violated the timeline of cosmic history the way a fully grown oak tree violates any explanation that it grew from an acorn planted last week. And the Webb telescope, with all its power and precision, was only just beginning to look. For the researchers who had flagged the anomalies, there was an unsettling arithmetic to contend with. The sample size in those first images was tiny. Webb had been operational for only a few months. The area of sky covered was a fraction of the total observable universe. And yet already, in that minuscule sample, the data contained objects that strained or exceeded the model's predictions. If the anomalies were real rather than instrumental artifacts, the statistical implication was stark. There should be many more of them, across the entire sky, at all the distances Webb had not yet examined. The universe might be filled with early massive galaxies that the standard framework had never predicted and could not explain. The first images had been a celebration, but for the people who knew what to look for, they had also been a warning. February 23rd, 2023. A paper landed in the journal Nature that changed the conversation from whispered concern to open confrontation. The authors were Ivo Labbé, an astronomer at Swinburne University of Technology in Australia, and Erica Nelson at the University of Colorado Boulder, along with a team of colleagues. They had been analyzing early James Webb Space Telescope photometric data, measuring the light coming from extremely distant objects, and what they had found was difficult to process even for the people who found it. 6 candidate galaxies, all of them existing between 500 and 700 million years after the Big Bang, and their masses, if the measurements held up, were extraordinary. Up to 100 billion solar masses, 100 billion times the mass of our own star. Some of these objects, if confirmed, would rival the Milky Way in size. The Milky Way took approximately 13 billion years to build. These candidates had apparently done something comparable in less than 1 billion years. Lambda Cold Dark Matter had a specific prediction for this era. Early galaxies should be small. They should be the building blocks, the seeds, the raw material from which larger galaxies would eventually be assembled over billions of years. They should look like infant clumps of gas and newborn stars. What the data seemed to show instead were fully grown adults, sitting in the cosmic nursery with no business being there. Joel Leger, a galaxy evolution researcher at Penn State University, read the paper and offered a verdict that spread quickly through the astronomical community. These objects, he said, were in tension with 99% of cosmological models. He did not say the models were wrong. He said, 99% of them could not account for what the data appeared to show. Erica Nelson, one of the paper's lead authors, put it more directly. "It's just crazy," she said, "that these things seem to exist." The community fractured along predictable lines. Established researchers who had built careers on Lambda Cold Dark Matter pointed to the error bars. Photometric measurements, they noted, are estimates derived from the color and brightness of light across several wavelength bands, not direct measurements. They could be wrong. They were often wrong. Redshift estimates made this way, called photometric redshifts, had fooled astronomers before. Maybe these objects were not as distant or not as massive as the data suggested. But the data was the data, and there were 6 of them. 6 candidate objects that each, individually, strained the models. 6 objects all found in a small early sample, before Webb had even begun its deep systematic surveys. The implication, if they were real, was not that cosmologists had made a minor error somewhere. The implication was that something fundamental about the early universe had been misunderstood. Something about how fast matter could organize itself into galaxies. Something about the conditions that existed in those first few 100 million years. The field had been split, and the instrument doing the splitting was only warming up. Science does not collapse under pressure. It argues back, and in the months following the Labbe and Nelson paper, the arguments came hard and fast, which is exactly how the process is supposed to work. The first line of attack was methodological. Photometric redshifts, critics pointed out, carry significant uncertainty. When you measure a galaxy's distance by analyzing how its light is distributed across different wavelengths, you are making an inference based on assumptions about what that galaxy's light should look like. Those assumptions can be wrong. Dust inside a galaxy absorbs blue light and re-emits it as red, making a galaxy look more distant than it actually is. Active galactic nuclei, the energetic cores of galaxies hosting massive black holes, can also inflate apparent brightness, making an object appear more massive than its stellar content alone would justify. One by one through 2023, researchers ran the candidates through the gauntlet of follow-up observation and independent analysis. Some of them did not survive. A handful of the most dramatic early claims were revised downward when better data arrived. The redshifts were not as extreme as initially estimated. The masses were more modest, within the range, uncomfortably large perhaps, but not the catastrophic outliers the first measurements had suggested. The skeptics felt vindicated. The models breathed again. Scientific Twitter, to the extent that is still a relevant measure of anything, declared the crisis overstated. Then came the spectroscopic confirmations, and that changed everything. Where photometric measurements estimate redshift by analyzing the overall color of a galaxy's light, spectroscopy breaks that light into its individual wavelengths and looks for specific chemical signatures. The absorption and emission lines of hydrogen, oxygen, carbon, magnesium. Each element has a known fingerprint in the spectrum, and when you find that fingerprint shifted to a longer wavelength by a calculable amount, you have a precise measurement of how fast the galaxy is receding, and therefore how far away it is. Spectroscopy does not estimate, it confirms. The galaxies that survived spectroscopic scrutiny in 2023 were fewer in number than the original photometric candidates. But they were real, verified not by one instrument or one team, but by multiple independent observations, all pointing to the same conclusion. These objects existed. They were as distant as the early measurements had suggested. Some were as massive, and none of the counter-arguments could explain them away. What the skeptical campaign had accomplished, ironically, was to sharpen the problem. By weeding out the candidates that could be explained, it left behind the ones that could not. The confirmed galaxies were not outliers at the edge of what the models could accommodate. They were, as researchers put it, genuinely anomalous. A few of them sat in regions of parameter space where no galaxy should exist if the standard model was correct. The field had spent a year trying to make the problem go away. It had not gone away. In some respects, it had gotten worse. There is an important distinction worth drawing here, because the popular press sometimes collapses it. The confirmed anomalies did not mean that all of Lambda Cold Dark Matter was wrong. The model's predictions about the composition of the universe, the proportions of dark matter and dark energy, remained in excellent agreement with other data. The problem was, specifically with the timeline of early galaxy formation, how quickly did matter organize itself? How fast did the first massive structures assemble? On those questions, and those questions alone, the Webb data and the model were beginning to diverge in ways that a year of skeptical pushback had failed to resolve. Something real was there. The community was no longer arguing about whether there was a problem. It was arguing about how big the problem was. That is a very different conversation. Faced with data that defied easy explanation, the James Webb Space Telescope science teams did what any good scientist does when confronted with an anomaly. They looked harder. The James Webb Advanced Deep Extragalactic Survey, known within the community by the name JADES, was the most ambitious imaging and spectroscopic program the telescope would undertake in its early years. The design was simple in concept and staggering in commitment. Point the telescope at two carefully chosen patches of sky, regions that had already been studied extensively by Hubble and ground-based observatories, and stare. Hundreds of hours of exposure time, multiple instruments. Every photon counted. Kevin Hainline at the University of Arizona led parts of the analysis, alongside Stefano Carniani at the Scuola Normale Superiore in Pisa, Italy, and a large international team. Their goal was not to hunt for individual spectacular objects. Their goal was systematic. Map the galaxy population in the early universe. Build a complete, statistically meaningful catalogue. Measure redshifts not by the dozens but by the thousands. Understand the architecture of cosmic history the same way a geologist understands rock strata, layer by careful layer. The survey delivered. Thousands of galaxies catalogued. Redshifts confirmed spectroscopically for objects reaching back to within the first few 100 million years of cosmic time. JADES became the deepest and most complete census of the early universe ever compiled. Researchers published paper after paper, each one adding resolution to the picture of how the cosmos evolved from a featureless fog into the structured web of galaxies that surrounds us today. Most of what JADES found was consistent with prior knowledge, filling in gaps and refining measurements. But some of what it found was not. Hidden inside the vast JADES catalogue, sitting at a redshift no one had previously confirmed, was a galaxy that did not fit. The data around it accumulated slowly, checked and rechecked by multiple team members who each kept expecting to find an error. There was no error. The object was real, and it was sitting at a distance and a cosmic age that, in the words of several of the researchers involved, should have been physically impossible. The team named it JADES GSZ 14-0, and the announcement of its confirmed properties, when it finally came, pushed past every boundary of what the standard model could explain. It broke the boundary entirely, in a way that no amount of revised error bars or alternative interpretations could repair. One of the core assumptions of modern cosmology had been tested, and the test had failed. The universe, it turned out, had been busy before anyone thought it could be. The catalogue entry that would carry the designation JADES GSC 14-0 was about to become one of the most discussed objects in the history of observational cosmology. The teams staring at its spectral data had already checked their work multiple times. They would check it again, and when they were done checking, the answer would still be the same: impossible and real. May 2024. The confirmation came through. The galaxy designated JADES GSZ 14-0 had a confirmed spectroscopic redshift of 14.32. That number requires translation to be felt properly. A redshift of 14.32 means that the light captured by the James Webb Space Telescope left this galaxy just 290 million years after the Big Bang. The universe, by the best current measurements, is 13.8 billion years old. 290 million years is roughly 2% of that total age. The universe was, cosmically speaking, a newborn, and this galaxy was already there. That alone was remarkable, but not entirely unprecedented for Webb. The telescope had been pushing the redshift record steadily upward since its first science release. But what made JADES GSZ 14.0 different was more than the question of when it existed. The deeper shock was what it contained. The galaxy spans 1,600 light-years across. Compare that to our own Milky Way, which stretches approximately 100,000 light-years from edge to edge, and JADES GSZ 14.0 sounds small, but remember the age. At 290 million years, it should not be 1,600 light-years. It should be a smudge. It should be a proto-galactic fragment, barely distinguishable from the surrounding intergalactic gas. Its stellar mass, approximately 500 million solar masses, was already enough to challenge the models of how quickly gas can collapse and ignite into stars. Then the spectroscopy revealed oxygen. Oxygen does not form in the Big Bang. The Big Bang produced hydrogen, helium, and trace amounts of lithium, and nothing heavier. Every other element in the periodic table was forged later, inside stars. Oxygen, specifically, is produced in the cores of massive stars and scattered into space when those stars end their lives in supernova explosions. For oxygen to be present in detectable quantities inside a galaxy, that galaxy must have already hosted at least one, and likely multiple, generations of stars that were born, lived out their full stellar lifetimes, and died violently. The standard model put that process at a minimum of 1 billion years. JADES GSZ 14.0 was doing it at 290 million years. Stefano Carniani, who led the analysis of the galaxy's spectral data, expressed the difficulty plainly. How can nature make such a bright, massive, and large galaxy in less than 300 million years? It was not a rhetorical question. He and his colleagues genuinely did not have an answer. Sander Schoes, of Leiden University, working on the same data, reached for an analogy. It is like finding an adolescent where you would only expect babies. The light from this galaxy traveled 13.4 billion years to reach the Webb mirror. Due to the expansion of the universe during that journey, the galaxy now sits at a proper distance of approximately 33 billion light-years from Earth. We are not looking at something that exists in the universe as it is today. We are looking at a message from a time before our planet, before our star, before most of the stars in the Milky Way were born. And that message says, we were already here. We had already lived and died and scattered our remains across space. Whatever came before us, you have not yet found it. The question hanging at the end of every conversation about JADES GSZ 14.0 was the same question. If oxygen was already present at 290 million years, then stars must have formed and ended their lives before we can currently observe what existed in that earlier period. What generated those first stars? And how much of cosmic history is hidden in a window the telescope had not yet opened? The astronomical community had barely absorbed the implications of JADES GSZ 14.0 when the next blow landed. In the weeks following the JADES confirmation, Peter Van Dokkum of Yale University and Rohan Naidu of the Massachusetts Institute of Technology announced a separate discovery, a galaxy at redshift 14.44. They named it MOME Z14. The subtitle of their published paper called it, without apparent irony, a cosmic miracle. Redshift 14.44 places this galaxy at 280 million years after the Big Bang, 10 million years earlier than JADES GSZ 14.0. which means slightly deeper into the epoch that Lambda Cold Dark Matter models least understood. And MOMZ-14 had its own set of properties that resisted all conventional explanation. The galaxy spans approximately 500 light-years across. That is a tiny footprint by any modern standard. But at 280 million years, it was not a featureless blob of young stars. It was structured, organized. The spectral data revealed a galaxy undergoing a powerful burst of star formation, converting gas into stars at a rate that, scaled to its size, was extraordinary. And unlike many other unusual early galaxies, MOMZ-14 showed no signs of an active galactic nucleus, no energetic black hole inflating its apparent brightness. The light was coming entirely from the stars, pure starburst. Lambda Cold Dark Matter's hierarchical formation scenario had a clear prediction for objects of this type. Massive, structured galaxies do not form early, they form late. They are assembled from the mergers of smaller galaxies over billions of years. The most massive galaxies in the present-day universe, the giant ellipticals sitting at the centers of galaxy clusters, earned their size slowly, consuming smaller galaxies across cosmic time. That is how the model worked. Small first, large later, always. MOMZ-14 violated this at every level. Consider the sharks comparison. Sharks have been swimming in Earth's oceans for approximately 450 million years. They existed before trees. They outlasted the dinosaurs. They are, by any measure of biological history, ancient. MOMZ-14 has existed for 280 million years. This galaxy is younger than sharks, and yet it already shows the structural complexity and chemical signature that the standard model predicted would take billions of years to develop. The spectral data from MOMZ-14 also revealed something else, something that would have seemed impossible before Webb began its deep surveys. The galaxy showed a high ratio of nitrogen to carbon, a chemical fingerprint that in the present-day universe is associated specifically with the densest, oldest stellar environments in the Milky Way. The globular clusters, ancient balls of stars that orbit our galaxy's halo and date back nearly to the beginning of cosmic time. Finding that signature in a galaxy at 280 million years old suggested that MOMZ-14 was not a primitive ancestor of later galactic structure. It was already chemically mature in ways that the models could not account for. Van Dokkum, Naidu, and their colleagues were careful with their language. They noted the uncertainties. They acknowledged that further observations would be needed. But they also called it a cosmic miracle, and they meant it in the technical sense. Something so statistically improbable under the current framework that its existence demanded a new framework. Two galaxies, weeks apart, both at the edge of observable time, both impossible under the best theory humanity had constructed to explain the universe. And the James Webb Space Telescope, sitting nearly 1 million miles from Earth, cooling itself to temperatures colder than deep space, had only just started looking. Whatever it would find next, the field would never again be able to look at the early universe and say it understood what had happened there. The comfortable certainty of Lambda Cold Dark Matter was over. The era of genuine, productive confusion had begun. The confusion was not a dead end. Confusion, in science, is a beginning. Every prediction that failed, every galaxy that arrived too early, every mass that exceeded what the universe should have allowed, each one was an arrow pointing somewhere new. The field had lost its certainty. What it gained, in exchange, was a far more interesting set of questions. One of those questions arrived in the form of light that had no business existing. JADESGS Z131 is a galaxy at redshift 13.0, which places it 330 million years after the Big Bang. That is already deep in territory where Lambda Cold Dark Matter struggles. But the redshift alone was not what stopped astronomers cold. It was what kind of light the galaxy was emitting. There is a specific ultraviolet wavelength called Lyman alpha radiation. It is produced when hydrogen atoms release energy after absorbing ultraviolet photons from young, hot stars. It is, in that sense, a signature of vigorous star formation, and in the early universe, it should be completely invisible to us. Here is why. The early cosmos was filled with neutral hydrogen gas, a thick fog stretching across billions of light years. That fog is extraordinarily efficient at one particular job, absorbing Lyman alpha radiation. Photons at that wavelength enter the fog and simply vanish. They are captured before they can travel. The standard model of cosmic history held that any Lyman alpha signal from before reionization was erased in transit. Period. JADESGS said 131 is shining in Lyman alpha. Kevin Hainline of the University of Arizona, one of the researchers analyzing the data, put it plainly: "We really shouldn't have found a galaxy like this." That sentence, understated and precise, carries the full weight of what the detection means. A signal the fog should have swallowed is arriving at our detectors. Somehow, the light got through. There are only a few ways this can happen. One possibility is that the galaxy itself created a bubble around it, a region where the surrounding hydrogen had already been ionized and cleared, allowing the Lyman alpha photons a path to escape. But for a bubble large enough to let this signal through to exist 330 million years after the Big Bang, ionizing radiation would have had to start burning through the fog far earlier than any model predicted. Another possibility is that the fog was never as thick as the models assumed, that the neutral hydrogen density in the early universe was lower, patchier, more transparent in certain regions than the standard timeline allows. Either interpretation leads to the same conclusion. The reionization of the universe began significantly earlier than cosmologists calculated. The scale of the revision matters. Every textbook account of early cosmic history includes a timeline for when the universe transitioned from opaque to transparent. That timeline was not a guess. It was derived from decades of observation, cross-checked against multiple independent datasets, and accepted as one of the firmest anchors in the chronology of the cosmos. JADESGSZ 131 is telling us that anchor is in the wrong place. And here is what makes it harder to dismiss. This is a direct detection. There is no inference chain, no model-dependent calculation standing between the telescope and the conclusion. The photons arrived. The wavelength was measured. The signal is Lyman alpha, from a time when Lyman alpha should not be able to reach us. The universe was not doing what it was supposed to be doing, and for the scientists studying these datasets, the question was no longer whether something was wrong with the standard picture. The question was how much was wrong and where exactly the errors had crept in. Now consider a different kind of wrongness. Consider the problem of looking directly at something and still misidentifying what it is. Before the James Webb Space Telescope launched, Hubble had already made history with a discovery that seemed almost impossibly dramatic. Astronomers using Hubble detected a single star at a redshift of 6.2, placing it roughly 12.9 billion light-years away. That made it the most distant individual star ever resolved. They named it Arundel, after a character from J.R.R. Tolkien's mythology, whose name meant morning star in Old English. The detection was possible because of gravitational lensing. A massive galaxy cluster between Arundel and Earth was bending and magnifying the light from behind it, the way a cosmic magnifying glass, aligning perfectly along a line called a caustic, can amplify a source by factors of thousands. Hubble had detected Arundel riding that caustic. Its light stretched and brightened until a single stellar object billions of light-years away became, briefly, visible. It was a genuine milestone, a single star, at 12.9 billion light-years. The press called it a record that might stand for years. Then James Webb looked at Arundel. What the telescope found was not what Hubble had implied. The brightness profile and the spectral signature of Arundel, analyzed with the far superior resolution and infrared sensitivity of James Webb matched the signature of a star cluster, a dense grouping of potentially hundreds or thousands of individual stars, packed closely enough together that at the distances and resolutions involved, they blur into what appears to be a single point of light. The record for most distant individual star observed may belong to an object that is not a single star at all. Think carefully about what this means for the broader enterprise of astronomy. The researchers studying ridddle were not careless. Hubble was functioning perfectly. The analysis was thorough and published in a peer-reviewed journal. The entire apparatus of scientific scrutiny had looked at this object and concluded one star, and that conclusion was wrong. If the best instruments and the most careful minds can look directly at something and misidentify its fundamental nature, then every observation becomes a question. Every caption under every image, every record claimed, every fact stated with confidence must carry an implicit asterisk, according to what we could resolve at the time. The problem here is epistemological, rooted in the nature of knowledge itself, not a crisis of competence. Science has always worked this way. Each generation of instruments reveals that the previous generation's certainties were approximations. But what James Webb is revealing is that some of those approximations were not close. They were categorically different from reality. Ridddle is not a footnote. It is a lesson about the relationship between observation and knowledge. We can point a telescope at a thing, measure it with every tool we have, name it, celebrate it, publish it in Nature, and still be fundamentally wrong about what we are looking at. That lesson matters, because as James Webb continued returning data, it would expose more cases where the confident conclusion and the actual reality were separated by a gap far wider than anyone had anticipated. There is a useful analogy here, though it is imperfect like all analogies. Imagine you are navigating by starlight at sea, a practice humans trusted for thousands of years. You learn the positions, you chart the courses, you sail confidently. Then someone hands you a GPS device and tells you that the star you relied on most has shifted, that atmospheric refraction had been bending its apparent position the entire time you were using it. Your navigation was internally consistent. Your charts were accurate relative to each other, but your fixed reference point was not where you believed it to be. Ridddle is that shifted star, a fixed reference, celebrated and relied upon, that the next instrument revealed to be something other than what it appeared. The universe does not hand out simple, clean signals. It hands out whatever it has and leaves the interpretation to us. Every interpretation is provisional. Every record, every headline, every superlative attached to an observation carries an expiration date, measured in the lifespan of the next instrument capable of looking more carefully. Every so often, science produces a number that becomes load-bearing, a single value that so much else depends on that if it shifts, the entire structure above it has to be reassessed. The Hubble constant is that kind of number, named after Edwin Hubble, who first measured the expansion of the universe in the 1920s. The Hubble constant describes the rate at which the cosmos is currently growing. Measure a galaxy's distance. Measure how fast it is receding from us. Divide one by the other. The result, expressed in kilometers per second per megaparsec, tells you how quickly space itself is stretching. Get that number right, and you can calculate the age of the universe, the rate of structure formation, the future of cosmic expansion. Get it wrong, and every model built on top of it is subtly corrupted. For decades, cosmologists argued about the Hubble constant. By the early 2020s, two methods of measuring it had emerged as the most credible, and they disagreed. The first method worked by looking backward in time. The Planck satellite had mapped the cosmic microwave background, the faint afterglow of the Big Bang, with extraordinary precision. From those measurements, physicists could calculate the early universe's expansion rate and extrapolate forward to the present day. The Planck result, 67.36 kilometers per second per megaparsec. The second method worked by measuring nearby objects directly. Adam Rees of Johns Hopkins University, a Nobel laureate, led a collaboration known informally as the supernova H0 for the equation of state team. Using Cepheid variable stars as distance markers and type Ia supernovae as standard candles, Rees and his colleagues measured the current expansion rate from local observations. Their result? 73.04 kilometers per second per megaparsec. The gap between those two numbers is approximately 5 to 6 kilometers per second per megaparsec. That sounds small. It is not small. The statistical significance of the discrepancy had reached 5 sigma. In particle physics, 5 sigma is the formal threshold for declaring a discovery. Flipping that, a 5 sigma disagreement between two measurements of the same quantity is the formal threshold for saying that something is seriously, possibly, fundamentally, wrong. Some physicists argued the discrepancy might be a systematic error in one or both methods. Perhaps the Cepheid measurements were contaminated by crowded stellar fields. Perhaps Hubble's resolution was insufficient to isolate individual stars cleanly. That was one reason the James Webb Space Telescope was directed to independently check the Cepheid measurements. With its vastly superior resolution, it could separate stars that Hubble had blurred together and potentially reveal whether the local measurement was inflated by error. In December 2024, Rees's team published their James Webb analysis. The result? 72.6 kilometers per second per megaparsec. Within measurement uncertainty, it confirmed the local value. The measurement error was not the problem. Daniel Skolnick of Duke University responded to the findings directly. The Hubble tension is now a Hubble crisis. Rees himself was precise about what remained. With measurement errors negated, what remains is the real and exciting possibility we have misunderstood the universe. 2 independent methods, 2 accurate measurements, 1 universe, 2 different answers. The crisis is real, and it is unresolved. Here is the question that keeps theoretical physicists awake. If the early universe and the late universe give you different expansion rates when measured by independent, verified methods, what does that actually mean? Lay people sometimes assume the discrepancy is a technical problem waiting to be cleaned up by better instrumentation. But the instruments have been checked, rechecked, and checked again. James Webb verified the local measurement. Planck's maps of the early universe are the most precise ever produced. The data is not corrupted. The methods are not confused. Something physical is causing the discrepancy, and identifying what that something is requires choosing between options that each break something the standard model currently considers settled. Option 1. There is unknown physics in the early universe. Perhaps in the first few 100,000 years after the Big Bang, some additional energy source gave the cosmos a kick, briefly accelerating expansion beyond what the standard model predicts. Mark Kamionkowski of Johns Hopkins University proposed exactly this, calling the hypothetical ingredient early dark energy. The idea is mathematically coherent. If a brief burst of additional energy existed in the early universe, it would shift the Planck-derived Hubble constant upward, closing the gap with the local measurement. The problem: early dark energy has never been detected. It leaves no confirmed observational fingerprint. It is a term added to an equation specifically because the equation produces the wrong answer without it. Adding undetected physics to explain a discrepancy is a move that must be made with great care, because at some point, a model that requires multiple invisible, unverifiable ingredients ceases to be a model of reality and becomes a sophisticated way of saying, we do not know. Option 2. There is unknown physics in the late universe. Perhaps dark energy, the force driving current acceleration, is not constant. Perhaps it changes over time in ways the standard model does not account for. Some early 2025 data from the Dark Energy Spectroscopic Instrument Survey suggested dark energy might be weakening. If confirmed, that would reshape the late universe expansion history and potentially close the gap from the other direction. Option 3 is the most radical. Perhaps the cosmological principle itself is incomplete. The cosmological principle states that the universe, at sufficiently large scales, is uniform and isotropic, the same in every direction, with no special axis, no preferred orientation. If that assumption breaks down, then using an early universe measurement derived under that assumption to predict a late universe measurement becomes formally invalid. The two answers diverge not because something is wrong with physics, but because the universe is not the kind of place the cosmological principle assumed it was. Each solution is serious. Each solution, if confirmed, would require rewriting chapters of cosmology that have been considered settled for decades. And the honest answer, as of early 2026, is that no one knows which option is correct. There is a deeper discomfort lurking beneath all three options. Every proposed solution to the Hubble tension requires the existence of something that has not been directly observed. Early dark energy is undetected. A time-varying form of late dark energy is as yet unconfirmed. A violation of the cosmological principle at the scales required remains unproven. Cosmology is being asked to choose between three types of unknown physics, without enough data to definitively rule out any of them. This is where the question of falsifiability becomes urgent. A scientific model is powerful precisely because it makes predictions that can be tested and, in principle, proven wrong. A model that can accommodate any result by adding additional invisible components is no longer making predictions in the most meaningful sense. It is making adjustments. The two look similar from the outside. From the inside, they are entirely different enterprises. Cosmologists are acutely aware of this risk, and the more honest ones will say so directly. The Hubble tension is forcing the field to ask whether it is still doing science the hard way, or whether it is starting to do something more comfortable and less honest. Before the confusion over individual galaxies, before the crisis in expansion rates, there was a process that the entire framework of early cosmic history depended on. It was called reionization, and James Webb has fundamentally altered what we thought we knew about when and how it happened. Reionization was the great transition. In the first moments after the Big Bang, the universe was a plasma of charged particles, opaque to light. Then it cooled. Neutral hydrogen formed. And for hundreds of millions of years, the cosmos went dark. No stars yet, no galaxies. Just hydrogen and helium gas drifting in gravitational wells, waiting. This period is sometimes called the Cosmic Dark Ages. Then the first stars ignited. Then the first galaxies formed. And the ultraviolet radiation pouring from those early sources began ionizing the surrounding hydrogen gas, breaking neutral atoms back into their component protons and electrons. As ionized bubbles grew and merged, the fog burned away, and the universe became transparent to visible light. That transition, from opaque to clear, is reionization. The established timeline held that reionization began around 400 to 500 million years after the Big Bang and was essentially complete by 1 billion years. This was not a rough estimate. It had been derived from observations of distant quasars, confirmed by Planck satellite data, and incorporated into the Standard Model as one of its firmest chronological anchors. James Webb's observations have shredded that timeline. Charlotte Mason, of the University of Copenhagen, one of the leading researchers on reionization, described the reaction in the field with characteristic understatement. Everyone was freaking out. The Lyman alpha detections from galaxies like J, A, D, E, SGSZ 131, combined with the sheer number of bright, energetic galaxies found in the first 500 million years, all point in the same direction. Reionization was producing clear regions of the universe far earlier than predicted. The process was moving faster than models allowed. By how much? A 2024 paper published in the monthly notices of the Royal Astronomical Society, one of the oldest and most respected journals in astronomy, put a number on it. Reionization, the paper concluded, ended approximately 350 million years earlier than models predicted. And then it went further. The paper stated directly, the Lambda Cold Dark Matter timeline simply cannot accommodate the combined James Webb and Planck observations, even if exotic fixes are introduced. That last clause is significant. Even if exotic fixes are introduced. The authors were not saying the model needed an adjustment. They were saying the model's timeline was incompatible with observation at a level that adjustments could not bridge. 350 million years earlier, in a universe 13.8 billion years old, that might sound like a small correction, but those 350 million years are not from the middle of cosmic history. They are from the very beginning, the first fraction of the universe's life, when conditions were most extreme and the foundational processes that shaped everything that came after were running at full speed. Getting that window wrong by 350 million years is not a small error in a large number. It is a large error in the most sensitive, consequential interval in cosmic history. The data kept arriving, the anomalies kept multiplying, and somewhere in the middle of it, the human cost of all this upheaval became visible in a single quotation from a working scientist. Alison Kirkpatrick is a professor of astronomy at the University of Kansas. She has spent her career studying galaxies in the early universe. She was trained in the framework of Lambda Cold Dark Matter. She taught it to her students. She built her research program on its predictions. She is, in that sense, entirely representative of a generation of cosmologists who entered the field when the standard model felt solid, who devoted the most productive years of their careers to its elaboration, and who are now watching its foundations shake. In 2023, Kirkpatrick said this, "Right now, I find myself lying awake at 3 a.m, wondering if everything I've ever done is wrong." That sentence landed differently for scientists than it did for the public. For non-specialists, it reads as a moment of self-doubt. For anyone who understands what it means to build a career in theoretical science, it reads as something closer to vertigo. Consider what it took to get to the point where Kirkpatrick was lying awake. Years of graduate school, learning the mathematics and the observational methods that underpin the standard model, a dissertation, postdoctoral positions, a faculty job won against fierce competition, courses designed and taught, graduate students mentored, papers published, grant proposals written, reviewed, funded, an entire professional identity constructed around a particular picture of how the universe works. And then the data starts saying that picture is wrong. The weight of it is real. It carries grief. The loss of certainty in something you have staked years on is genuinely painful. Some of that is ego, yes, but much of it is simply the disorientation of finding that the map you have been using to navigate does not match the territory. It also carries something else. Kirkpatrick has spoken publicly about the anxiety, and also about something she did not expect, the exhilaration, because if the map is wrong, the territory is more interesting than anyone knew. The career you thought you had, exploring the known corners of a mostly understood universe, turns out to be something far more open, far more uncertain, far more alive. That is science working exactly as it should. The discomfort is not a failure of the system. It is the system functioning correctly, producing data that challenges assumptions, forcing revision, creating the productive disorientation that precedes genuine understanding. But it is still, on a purely human level, frightening. To wake at 3 a.m. and wonder whether your map of reality needs to be redrawn is not an abstract philosophical problem. It is something you feel in your body. Kirkpatrick's sleepless nights are not hers alone. They belong to an entire generation of scientists who are living through the most significant revision of cosmological understanding in decades, and who must do so while teaching, publishing, and advising, while continuing to operate as if the ground beneath them is solid, even as they watch it shift. There is a specific category of mystery that reveals the limits of the human mind's pattern recognition ability, and James Webb has produced one of the finest examples of it in modern astronomy. Scientists called them little red dots. The name is accurate and unassuming. When James Webb's first deep field images came back, a new population of compact, extremely red objects appeared distributed through the early universe, clustered in the first billion years of cosmic history. They were small, they were bright, they were very, very red, and they fit no existing category. By 2024, 341 of them had been catalogued. Over the following 3 years, the scientific community proposed 4 distinct explanations for what they were, and each explanation ran into serious trouble. In 2022, the leading hypothesis was that little red dots were compact starburst galaxies, extremely dense regions of furious star formation whose ultraviolet emission had been redshifted into the infrared by the expansion of the universe. It was a reasonable first guess. Spectroscopic analysis refuted it. The spectral signatures did not match. Between 2023 and 2024, attention shifted to active galactic nuclei, galaxies with supermassive black holes at their centers that were actively accreting gas and radiating enormous amounts of energy across the electromagnetic spectrum. Feeding black holes are X-ray sources. They produce X-ray emission as a reliable signature of their accretion activity. If the little red dots were active galactic nuclei, they should appear in X-ray surveys. Of 341 catalogued objects, exactly 2 were detected in X-rays. 2. That hypothesis was refuted. In September 2025, a third theory emerged: black hole stars, a theoretical class of object in which a black hole forms the gravitational core of an enormous ball of gas, powering the whole structure from the inside. Objects of this type had been theorized but never observed. The hypothesis remains unconfirmed. Then, in January 2026, 2 independent papers arrived simultaneously from opposite sides of the Atlantic, and they disagreed with each other. A team at the Niels Bohr Institute in Copenhagen published in the journal Nature. Little red dots are young black holes wrapped in cocoons of dense ionized gas. The cocoon absorbs and reprocesses radiation, explaining the extreme redness and the absence of X-ray signatures. The same week, researchers at the Harvard-Smithsonian Center for Astrophysics published their analysis. Little red dots may be supermassive stars of approximately 1 million solar masses each, metal-free objects of a type that has never been directly observed, sometimes theorized as possible precursors to the first supermassive black holes. 2 papers, 2 research teams, 2 entirely different identities for the same population of objects. No consensus. 4 theories, 3 years, 341 unexplained objects. The scientific process is working. Each wrong answer narrows the search space, but every time the field thought it had a solution, the universe disagreed. Consider the human scale of this failure to agree. Hundreds of researchers across dozens of institutions have devoted years of work to these objects. Graduate students have written dissertations about them. Observing time on the most expensive scientific instrument ever built has been allocated to them. Peer-reviewed papers, each representing months of analysis and careful argument, have proposed and defended each successive theory. The community is not failing from lack of effort or expertise. It is failing because the objects themselves do not fit the categories built by the physics that came before them. That is what a genuinely new phenomenon looks like in real time. It is not a clean discovery, with a press release and a Nobel Prize waiting at the end of a tidy chain of reasoning. It is this: 4 years of increasingly confident wrong answers, 2 simultaneous contradictory correct answers, 341 objects sitting in the data, refusing to be neatly explained. What James Webb has shown, in the case of the little red dots, is that the early universe was doing something with its mass and energy that no living physicist predicted. That realization carries weight that a number or a press release cannot fully convey. While astronomers were cataloging little red dots and measuring expansion rates, a quieter anomaly was accumulating in a different dataset. It was the kind of finding that, if it holds up, would require revising something even more fundamental than the timeline of reionization or the mass of early galaxies. It would require revising the most basic assumption cosmology makes about the nature of the universe itself. The cosmological principle states that the universe, at large enough scales, is isotropic and homogeneous. Isotropic means it looks the same in every direction. Homogeneous means its properties are the same everywhere. There is no special location in the universe, no special axis, no preferred direction. The universe, seen from far enough away, has no handedness. This principle is not merely a philosophical preference. It is the mathematical foundation beneath the standard model of cosmology. The equations that describe cosmic evolution, including the calculations from which the Lambda Cold Dark Matter model is derived, assume isotropy. Pull that assumption out, and the entire formal structure needs to be rebuilt from different starting conditions. Then, astronomers analyzed the rotation directions of the earliest galaxies in the James Webb Advanced Deep Extragalactic Survey, and the numbers came out strange. Galaxies, like storms and planets, can rotate in two directions. In a universe with no preferred axis, you would expect those rotations to be distributed randomly, roughly half clockwise, roughly half counterclockwise. Lambda Cold Dark Matter is explicit on this point. The ratio should be 1:1. Among the earliest observed galaxies in the survey, approximately 2/3 appeared to rotate clockwise, a 2:1 ratio. If that result is confirmed through further observation and independent analysis, the implications are severe. A 2:1 preference for clockwise rotation in the earliest galaxies would mean the universe inherited a directional bias from the Big Bang itself. The cosmos would have a memory. It would have, in the most literal possible sense, a handedness. Scientists are appropriately cautious. The sample size is not yet large enough to declare this a definitive discovery, and systematic errors in measuring rotation directions at cosmological distances are real and not trivial. Independent confirmation is required before conclusions can be drawn, but the finding is being taken seriously, and if it holds, it does not merely add another anomaly to the list. It calls into question whether the cosmological principle, which underlies the entire theoretical framework cosmologists have been using to analyze every other anomaly on this list, is actually true. To understand why this matters so profoundly, it helps to think about what the cosmological principle does for cosmology. It functions as far more than a background assumption. It is the license that allows scientists to extrapolate from local observations to universal conclusions. When a cosmologist measures the expansion rate in one region of the sky and declares that it describes the universe as a whole, that extrapolation is only valid if the universe is indeed the same in all directions. If it is not, if it has a preferred axis, a memory of its initial conditions, then every such extrapolation becomes suspect. The measurements are still accurate. The conclusions drawn from them, however, may not be. A universe with a handedness would be a universe that remembers what it was at the moment of its birth. That memory would be encoded in the rotation of the first structures to form, passed down through billions of years of cosmic evolution, visible today in the spin directions of galaxies that condensed from the original asymmetric conditions. It would mean the Big Bang was not perfectly symmetric. It would mean the universe we inhabit has an orientation, a direction it leans, inherited from a beginning that was less uniform than the standard model requires. And it would mean that cosmology, for all its precision, has been making calculations on a foundation it assumed was level, without ever verifying that assumption directly. Faced with all of this, a significant group of cosmologists has pushed back, strongly, intelligently, and they are worth listening to. The case for Lambda Cold Dark Matter is not simply the case of a theory refusing to die. It is the case for a model that has successfully predicted and explained an enormous range of phenomena across billions of years of cosmic history. The cosmic microwave background temperature fluctuations, the large-scale structure of the universe, the distribution of galaxy clusters, the abundance of light elements produced in the first minutes after the Big Bang. Across all of those measurements, Lambda Cold Dark Matter performs extraordinarily well. That record does not evaporate because James Webb found some large galaxies. The defenders of the Standard Model make several serious arguments. First, mass estimation in the early universe is genuinely difficult. The techniques used to infer stellar mass from the light of early galaxies involve assumptions about dust, star formation history, and stellar population that introduce real uncertainties. Some of the most extreme early mass estimates may be systematically inflated. Second, contamination. In the early universe, active galactic nuclei, those feeding supermassive black holes, can outshine the stellar mass of their entire host galaxy by orders of magnitude. If a massive early object contains a bright active galactic nucleus that is not correctly accounted for, its apparent stellar mass will be dramatically overestimated. Several of the most alarming cases of early massive galaxies have, upon closer inspection, shown signatures of active galactic nucleus contamination. Third, selection bias. James Webb was designed to detect the brightest, most luminous objects at high redshift. Bright, luminous objects are, by definition, the extreme outliers of any distribution. Lambda Cold Dark Matter allows for some fraction of unexpectedly massive early galaxies. If James Webb is pointing at those extreme objects because they are the only ones bright enough to detect, the survey may be constructing a portrait of the early universe from its rarest exceptions. Garth Illingworth of the University of California, Santa Cruz, one of the most experienced galaxy observers in the world, framed his own puzzlement honestly. How do you do this in the universe at such an early time? How do you form so many stars so quickly? His question is genuine. It is not a dismissal. It is a scientist confronting data that surprises him and asking the right question about it. These arguments are serious. They are made by serious people, and for each individual anomaly, they provide at least a plausible path toward reconciliation with the Standard Model. The difficulty is that the anomalies are not arriving one at a time. They are arriving together from independent observations, using independent methods, pointing in the same direction. For every galaxy, the defense explains away with dust corrections. A new one appears that resists that explanation. For every mass estimate that turns out to be contaminated by an active galactic nucleus, another galaxy remains with no obvious contamination and still too much mass. The individual rebuttals are credible. The cumulative pattern is harder to dismiss. 40 years is a long time to be wrong. Or rather, 40 years is a long time to be right and have no one listen. In 1983, an Israeli physicist named Mordechai Milgrom published a paper that proposed something radical. He was trying to explain an observation that had been troubling astronomers for years. Galaxies rotate at speeds that should, by the laws of gravity as understood at the time, tear them apart. The outer regions of galaxies move faster than they should given the visible mass. The standard explanation, which became the core assumption of Lambda Cold Dark Matter, was that invisible dark matter provides the additional gravitational pull. Milgrom proposed something different. Instead of adding invisible matter, he proposed modifying the law of gravity itself. Specifically, he proposed that at very low accelerations, far below what we experience anywhere in the solar system, gravity does not follow Newton's inverse square law. It behaves differently. It falls off more slowly with distance. The result, the outer regions of galaxies feel more gravitational pull than standard Newtonian dynamics would predict, without any dark matter required. He called the framework modified Newtonian dynamics. For the next 4 decades, mainstream cosmology largely ignored it. Lambda Cold Dark Matter was extraordinarily successful. It matched the cosmic microwave background. It reproduced large-scale structure. Dark matter was the preferred explanation, and modified Newtonian dynamics was treated as a curiosity, a model that might explain galaxy rotation curves but failed to account for larger-scale phenomena. it was relegated to the scientific margins, cited mainly by a small community of researchers who kept refining it while the rest of the field moved on. James Webb changed the calculation. The galaxy rotation anomalies observed in early universe surveys, the failure of dark matter simulations to reproduce the number, mass, and structure of early massive galaxies, the reionization timeline crisis. All of these are problems for a dark matter framework. Modified Newtonian dynamics predict some of them naturally, without the need for hypothetical particles that have never been directly detected despite decades of searching in underground laboratories and at particle colliders. This does not mean modified Newtonian dynamics is correct. Its own unresolved problems are real. It struggles to explain the behavior of galaxy clusters without invoking some form of additional mass. It has not produced a fully relativistic formulation that can be tested against the cosmic microwave background with the same precision as Lambda Cold Dark Matter. There are observations it cannot explain as neatly as its proponents would like. But a theory that spent 40 years in the scientific wilderness is suddenly, undeniably, back at the table. Researchers who were once told they were wasting their time are now being invited to collaborate. Their predictions are being tested against James Webb data with genuine openness. The dismissal is over. What does it mean when an alternative that was marginalized for 4 decades turns out to have been pointing towards something real? It means the mainstream was wrong to dismiss it. It means the social dynamics of science, the prestige hierarchies, the funding structures, the publication incentives that collectively decide which ideas receive resources and which are starved of attention. Those dynamics failed. For 40 years, they failed Milgrom and everyone who worked on modified Newtonian dynamics. The ideas survived anyway, kept alive by a small community operating at the edges of the field, waiting for data that would force the center to listen. The James Webb Space Telescope did not vindicate modified Newtonian dynamics, but it forced cosmology to stop pretending the alternative did not exist. So the field was forced to reckon with an alternative it had long dismissed. But something else was already happening inside the mainstream. The theorists had not been idle. While the critics were sharpening their arguments, a different group of physicists had quietly constructed a repair kit for Lambda Cold Dark Matter. The kit had a name: Early Dark Energy. And the moment you understand what it actually is, a single unsettling question takes shape. At what point does fixing a model become abandoning it? Mark Kamienkovsky at Johns Hopkins University proposed the idea with colleagues in the years leading into the 2020s. The logic went like this. The Hubble tension, that stubborn disagreement between the expansion rate measured from the ancient cosmic microwave background and the rate measured from nearby galaxies, could theoretically be resolved if the early universe contained an additional form of energy. Something that existed only briefly, shortly before the formation of the first atoms. A brief surge of repulsive energy that slightly accelerated expansion in those first 380,000 years, then faded away completely, leaving no trace. If that surge existed, the cosmic microwave background measurements would yield a slightly different Hubble constant, one that, once you account for the early boost, reconciles with the higher local measurements. The tension dissolves, the model survives. The physics community received early dark energy with cautious interest. Some papers found it plausible, some found it promising. The Hubble tension was a real problem, and this was at least a structured response. But then came the harder question, the one that has no clean answer. Has anyone ever detected early dark energy? No. It has never been observed. There is no direct evidence it exists. There is no predicted signature that has been confirmed in the data. Early dark energy is inferred from the gap between two numbers that refuse to agree. It is, in the most precise scientific sense, a postulate invented to preserve an existing framework. And here is where the discomfort becomes structural. Lambda Cold Dark Matter already requires two invisible, undetected ingredients. Dark matter, which accounts for 27% of the universe's mass and energy, has never been directly observed in any laboratory on Earth. dark energy, which accounts for 68% of everything, is inferred entirely from the accelerating expansion of space, and its physical nature remains completely unknown. Ordinary matter, everything you can see, touch, or measure directly, makes up only 5% of the universe. Lambda Cold Dark Matter describes. Add early dark energy, and the model now requires 3 separate undetected components, 3 invisible pillars holding up the architecture. Each one, individually, is scientifically defensible. Indirect evidence for dark matter is strong. The case for dark energy is real. Early dark energy at least addresses a genuine anomaly. But standing back and looking at the structure as a whole, something uncomfortable comes into focus. A model that explains the universe almost entirely through ingredients that cannot be directly detected or characterized is a model that is very difficult to falsify. And a model that cannot be falsified is, at some level, a model that cannot be tested. That is not a reason to reject Lambda Cold Dark Matter. It is a reason to take seriously the question of what scientific explanation actually means. Kamionkowski and his collaborators know this. They are not naive about the epistemological weight of what they have proposed. The field knows it. In the background of every workshop and conference where early dark energy is discussed, the same tension lives. Patching a model is legitimate science until the patches outnumber the original structure. At that point, you are not defending a theory anymore. You are building a new one, piece by piece, while calling it the old one. The question the field has not answered is simple. How many patches are too many? Let the mainstream patches settle for a moment. Because on a different shelf of the same theoretical library, a far stranger idea has been gathering support, a hypothesis that starts with a simple question. What if the universe did not wait for stars to die before it built its first black holes? The standard picture of black hole formation runs through stellar death. A massive star exhausts its fuel. Gravity wins. The core collapses. A black hole forms. It is a process measured in millions of years of stellar evolution. Lambda Cold Dark Matter predicts that the earliest black holes formed this way, and then grew gradually by consuming surrounding matter over billions of years. James Webb keeps finding supermassive black holes in the earliest epochs of the universe that are too large for this story. Black holes containing hundreds of millions or billions of times the mass of our star, already fully grown in a universe that is only a few 100 million years old. The standard formation pathway cannot produce objects that massive that quickly. The numbers simply do not work. The primordial black hole hypothesis offers a radically different origin story. In the first fractions of a second after the Big Bang, space was not smooth. It was violently uneven, shot through with regions of extreme density fluctuating against regions of relative emptiness. Scientists theorize that wherever density fluctuations exceeded a critical threshold, gravity could have overwhelmed the outward pressure of the newborn universe and collapsed those regions directly into black holes. With no stars required, no stellar evolution, no millions of years of waiting, these primordial black holes would have existed from nearly the beginning. Their mass could span an enormous range. Some theoretical estimates allow for primordial black holes as small as a fraction of a gram. Others, formed from larger density fluctuations, could have carried masses millions of times that of our star from the moment of their formation. If the most massive primordial black holes existed early enough and in sufficient numbers, they would have served as gravitational scaffolding. Matter falling toward them would feed the black holes, yes, but it would also pile up in surrounding halos, compressing gas, triggering star formation at rates that standard models cannot generate. The result would be galaxies that assembled far faster than Lambda Cold Dark Matter's hierarchical model allows, exactly the kind of galaxies James Webb keeps finding. The hypothesis does not stop there. Primordial black holes of certain mass ranges could also account for a portion of the dark matter budget. If enough of them formed with masses in the right range, They would behave gravitationally like dark matter, clumping, attracting ordinary matter, bending light, without emitting any radiation detectably. Some researchers have proposed that primordial black holes in a specific mass window could constitute a meaningful fraction of the dark matter Lambda Cold Dark Matter requires, but cannot identify. Avi Loeb at Harvard has been among the more vocal advocates for taking this hypothesis seriously as an observational target. Others in the field are more cautious, noting that constraints from gravitational microlensing and the cosmic microwave background have already ruled out primordial black holes as the dominant form of dark matter across most mass ranges. The truth is, the hypothesis remains genuinely unconfirmed and genuinely unrefuted. Primordial black holes have not been directly detected, but no observation has conclusively ruled them out either. And given that James Webb is finding objects that no other hypothesis explains cleanly, the idea that the universe seeded itself with black holes before the first stars ignited has moved from fringe speculation to serious scientific contention. What would it mean if they exist? It would mean the universe arrived pre-structured, pre-wired with gravitational seeds from its very first moments. It would mean the architecture of everything visible, every galaxy, every cluster, every filament, traces back to turbulence in the first fraction of a second of existence. That is either an answer or the opening of a vastly deeper question. Step back. Step all the way back. Forget the specific anomalies for a moment. The early galaxies, the Hubble tension, the spinning clusters. Ask instead a question that cuts across all of science, across cosmology and physics, and every field where grand models have eventually met their limits. In the history of human knowledge, what has it actually taken for a great theory to fall? The answer, when you look at the historical record carefully, is not a single devastating experiment. It is almost never that clean. Great theories fall slowly, then suddenly. Consider Newton. Newtonian gravity was the most successful scientific theory in human history at the time of its dominance. It predicted planetary orbits with extraordinary precision. It explained the tides. It launched the industrial age. And then astronomers tried to use it on Mercury, the planet closest to our star orbits in a slightly different path than Newton predicted. The discrepancy is tiny, only 43 arcseconds per century. A number so small it sounds like a rounding error, but it was real and reproducible, and no adjustment to Newtonian mechanics could make it disappear. It took 40 years of discomfort before Einstein's general relativity arrived to explain it. Consider the static universe. Before Edwin Hubble's redshift measurements in the 1920s, the dominant assumption was that the cosmos existed in a permanent steady state. Einstein himself installed a cosmological constant into his equations specifically to prevent his own theory from predicting an expanding universe, because an expanding universe was conceptually uncomfortable. Then Hubble published his data. The universe was expanding. The static model did not slowly yield. It collapsed overnight. Consider the steady-state model of the 1950s, championed by brilliant physicists including Fred Hoyle, who argued that the universe had no beginning, that matter was continuously created to maintain a constant average density as space expanded. The steady-state model had genuine predictive power and elegant simplicity. It died when Arno Penzias and Robert Wilson detected the cosmic microwave background radiation in 1965, the afterglow of a hot, dense beginning that steady-state cosmology had no room for. The pattern across all three cases is the same. The anomalies were present for years, sometimes decades, before the paradigm shifted. The defenders of the old model were not stupid. They were often the most rigorous scientists in the field, fighting hard for an explanation that had worked brilliantly before. The shift came when the weight of unexplained observations reached a threshold that no patch could address. Lambda Cold Dark Matter has survived challenges before. The missing satellites problem, the too big to fail problem. various tensions between simulations and observations that, over time, were resolved through better modeling of baryonic physics. The model adapted. The model endured, but the rate of anomalies arriving from James Webb is qualitatively different from anything in recent memory. In the first 3 years of scientific operation, the telescope generated more significant challenges to the standard cosmological model than the previous decade of combined observations. The anomalies are not clustered in one area. They span galaxy formation, black hole growth, chemical evolution, the expansion rate, and large-scale structure. They arrive across different instruments, different research groups, different methodologies. History says the model will likely survive, but history also says that when the anomalies are varied enough, and consistent enough, and resistant enough to individual explanation, the model that survives does so by becoming something different from what it was. The question is not whether Lambda Cold Dark Matter will change. The question is how much. The press releases always sound the same: confident language, carefully hedged conclusions, scientists speaking in the passive voice about what the data suggests, what the observations are consistent with, what requires further study. The public face of cosmology in 2026 is composed and calibrated. It projects an image of a field managing complexity in an orderly fashion. Go to the conferences, read the working papers, talk to researchers off the record. A different picture emerges. The field is not unified. It is not quietly confident. Inside the community, there is a real and widening distribution of opinion about what James Webb's findings actually mean, and where cosmology stands right now. One group, probably still the majority, believes Lambda Cold Dark Matter will survive. Their argument is not complacency, it is historical track record. The model has been challenged before, and has absorbed the challenge each time through improvements in simulation, fidelity, and a better understanding of star formation physics. The early galaxy anomalies, in this view, reflect the complexity of gas dynamics and feedback processes in the early universe, not a failure of the underlying cosmological framework. These researchers are not dismissing Webb's findings. They are betting that sufficient computational refinement will bring the simulations back into agreement with the observations. A second group believes Lambda Cold Dark Matter requires fundamental revision rather than incremental adjustment. These researchers point to the number, variety, and consistency of the anomalies as evidence that the model's core assumptions, and not merely its secondary parameters, are under strain. They are not predicting imminent revolution. They are arguing that the field needs to seriously investigate modifications to the dark matter prescription, alternatives to cold dark matter, and potentially revised treatments of how dark energy behaves across cosmic time. A third group, smaller but growing, uses a word that mainstream cosmology avoids: paradigm shift. These researchers argue that the accumulation of James Webb anomalies, taken together with the Hubble tension and the large-scale structure discrepancies, points toward a fundamental incompleteness in the current model, one that cannot be patched, only replaced. What is striking about the distribution is the proportion occupying the middle. A large fraction of working cosmologists, when asked privately, do not know which of these groups is right. They are genuinely uncertain. They are continuing to publish, continuing to refine, continuing to work within Lambda Cold Dark Matter, because that is the framework that has tools and predictions and a community. But the certainty that characterized the field after the cosmic microwave background measurements of the early 2000s has quietly eroded. One senior cosmologist, speaking at a workshop in 2024, put it plainly: the data is telling us something. We don't agree on what. That kind of honesty is not weakness in a scientific community. It is precisely the condition that precedes a productive reckoning. The consensus is not cracking dramatically. It is developing fissures, fine lines that run through the conference rooms and seminar halls and private email threads of the field. None of them is a break yet, but each new James Webb data release adds pressure to the same places. Fissures, under sufficient pressure, become fractures. Here is a question that sounds simple until you try to answer it precisely. How old is the universe? Ask a physicist in 2005, and they will tell you with calm authority 13.7 billion years, plus or minus a small margin. Ask one in 2026, and the honest answer has become more complicated. The number on paper is 13.8 billion years, derived from Lambda Cold Dark Matter's best fit to the cosmic microwave background data. But behind that number is a chain of assumptions, and James Webb has been pulling on several of those links simultaneously. The problem starts with the Hubble constant. If the universe is expanding faster than Lambda Cold Dark Matter predicts, as local measurements increasingly suggest, then running the expansion backward to find the beginning yields a shorter time. A higher Hubble constant means less time since the Big Bang. Some estimates consistent with the local measurement put the universe's age closer to 12.5 or 13 billion years, not 13.8. That alone would be interesting. But James Webb added a second layer of complexity. The telescope has observed ancient globular clusters, dense, spherical collections of hundreds of thousands to millions of stars that formed in the earliest epochs of galaxy formation. Some of these clusters, when their stellar populations are analyzed, appear to be extraordinarily old enough that their age, under certain measurement methods, approaches or creates tension with the 13.8 billion year figure. A universe cannot contain objects older than itself. If globular cluster ages are being measured correctly, and the universe is as young as the high Hubble constant implies, something in the accounting does not balance. One proposed resolution is deeply unconventional. A paper published in the monthly notices of the Royal Astronomical Society put forward what its authors called the covariant coupling constants plus tired light model. Under this framework, fundamental physical constants were different in the early universe, and light loses energy as it travels across cosmic distances through a mechanism distinct from redshift caused by expansion alone. The model's authors suggest it accommodates the James Webb observational data more naturally than Lambda Cold Dark Matter, and their estimate for the age of the universe is 26.7 billion years. Mainstream cosmology does not embrace it. The covariant coupling constants plus tired light model is considered fringe by the overwhelming majority of working cosmologists. Standard tired light theories have been ruled out through multiple independent observations. But the paper was peer-reviewed, published in a major journal, and its authors argued their modified version addressed the traditional objections. The significance is not that the 26.7 billion year figure is correct. The significance is that the age of the universe, which most people assume is a solved problem, is currently a subject of genuine scientific dispute in a way it has not been for more than 3 decades. Textbooks present 13.8 billion years as settled. The frontier presents something messier, when the answer to how old the universe is depends on which dataset you trust, and different datasets keep disagreeing. The question is open. There is a number that appears in almost every Lambda Cold Dark Matter summary without much comment: 27%. That is the share of the universe's total mass and energy that is dark matter. Not ordinary matter, something else entirely, something that has never been directly detected by any instrument ever built. Physicists infer dark matter's existence through its gravitational effects. Galaxies rotate too fast for their visible matter alone to hold them together. Clusters of galaxies deflect light by amounts far exceeding what their visible mass could produce. The large-scale structure of the cosmic web, the filaments and voids that span hundreds of millions of light-years, only forms in computer simulations when dark matter is included. The indirect evidence is strong. The cumulative case is genuinely compelling. But James Webb has been straining the simulations that use cold dark matter to generate those structures. Cold dark matter, by definition, moves slowly. It clumps readily at small scales. It builds structure from the bottom up, small halos merging into larger ones over billions of years. Lambda Cold Dark Matter's hierarchical structure formation model predicts a specific distribution of galaxy sizes and masses at different epochs of cosmic history. The galaxies James Webb is finding at redshifts above 10 do not match that distribution. They are too massive, too structured, too chemically evolved for their age. The simulations that use cold dark matter as their scaffolding cannot reproduce them. Researchers have spent 3 years asking whether better stellar physics can close the gap. Some of it can, not all of it. 3 explanations are currently in circulation. First, cold dark matter is correct, and the discrepancy is entirely in the baryonic physics. The gas, the stars, the feedback processes, all of which are complex and imperfectly modeled. More computation and better subgrid physics will eventually bring the simulations into line with observations. Second, dark matter is real, but it is not cold. A warmer, fuzzier, or self-interacting form of dark matter would cluster differently at small scales, potentially producing fewer small halos and allowing large structures to form in ways that better match the James Webb data. Warm dark matter and fuzzy dark matter are both scientifically active alternatives, each with their own theoretical frameworks and observational predictions. Third, dark matter, as conventionally conceived, does not exist, and something fundamentally different is generating the gravitational effects attributed to it. 5 years ago, the third option was not discussed seriously at major conferences. It was the domain of a small number of theorists working outside the mainstream. Today, it appears in papers submitted to the leading astrophysical journals. The change in tone is gradual, but it is real. The third option has not become mainstream. It has become discussable. That shift, from undiscussable to discussable, is how revolutions begin. Here is the assumption buried so deep in cosmology that most textbooks do not identify it as an assumption. The universe, at large enough scales, is the same everywhere and in every direction. Statistically smooth, statistically uniform, isotropic and homogeneous across the full observable volume. This is the cosmological principle. It is the foundation beneath the foundation. Einstein's equations, applied to the universe as a whole, cannot be solved without it. Without uniformity at large scales, the mathematics of cosmic expansion becomes intractable. The entire machinery of modern cosmology, the Friedmann equations, the cosmic microwave background predictions, the structure formation simulations, runs on top of this assumption. It has never been directly verified. It is, in the truest sense, an axiom chosen for practical necessity and supported by the general smoothness of the cosmic microwave background. James Webb has been contributing, indirectly but persistently, to a growing body of evidence suggesting the cosmological principle may be more fragile than assumed. The clockwise galaxy rotation asymmetry, published and debated over the past several years, found that galaxies in one region of the sky rotate preferentially in one direction, an effect that should be statistically absent if the cosmological principle holds. The Hubble tension itself carries a hint of directionality in some analyses, with the expansion rate appearing slightly different depending on which part of the sky local measurements are drawn from. Then there is the large-scale structure. The Hercules Corona Borealis Great Wall, a structure of galaxies and clusters spanning roughly 10 billion light-years, is larger than the cosmological principle predicts should exist. Simulations built on Lambda Cold Dark Matter do not produce structures of that scale. The South Pole cold spot in the cosmic microwave background remains unexplained after decades of analysis. The axis of evil, an alignment of features in the cosmic microwave background that appears to correlate with the plane of our solar system, has resisted dismissal. Each anomaly, taken alone, is manageable. Taken together, they form a pattern. A pattern suggesting the universe may have preferred directions, preferred scales of structure, preferred asymmetries that a perfectly uniform cosmos should not possess. If the cosmological principle is even slightly violated, the consequences for cosmology are not minor. Every inference drawn from the assumption of uniformity becomes suspect. The derived age of the universe, the inferred expansion history, the calculated matter density, all of these rest, ultimately, on the universe being statistically the same everywhere. James Webb is not primarily a survey telescope. It points deep into specific patches of sky, but the structures it finds, the overdensities, the early clusters, the unexpected filaments, consistently suggest a universe that is more structured, more organized, and more directionally uneven than the cosmological principle allows. No one has declared the principle broken. The field is not ready to take that step, but the question is being asked with increasing seriousness by researchers who, 5 years ago, would not have entertained it. When the foundation of an edifice shows fine cracks, you do not immediately conclude the building will fall, but you do begin to study the cracks. Consider for a moment the engineer who spent 15 years designing a component of a telescope, retired in 2019, and watched the launch from home on a screen 2 years later. Consider the astronomer who wrote her doctoral dissertation on what James Webb would find, using simulations based on Lambda Cold Dark Matter, and is now 32 years old, sitting with data that her dissertation did not predict. Consider the graduate students who enrolled in cosmology programs in 2019 because they wanted to work on James Webb data, who were told the framework was mature and their job would be to fill in the details. They are now facing the possibility that the details do not fit, and the possibility that rebuilding the framework might be their generation's actual work. There is a particular human cost to scientific revolution that does not appear in the papers. It is not the cost of being wrong. Scientists are trained, intellectually, if not emotionally, to accept being wrong. The deeper cost is the cost of unlearning. A researcher who spent a decade developing sophisticated intuitions about how galaxies form under Lambda Cold Dark Matter, who built those intuitions into models and papers and teaching, faces a specific kind of loss when the data suggests the intuitions need to be dismantled and rebuilt. Revision is, in one reading, the finest thing science asks of its practitioners, the ability to update without breaking. But it is also genuinely hard. Careers are built on frameworks. Grant applications reference them. Teaching curricula encode them. Collaboration networks form around shared assumptions. When the assumptions shift, all of it shifts with them. The engineers who built James Webb and did not live to see its first light are part of this story too. The telescope was first proposed in 1996. It launched in 2021, 25 years. The people who conceived it imagined it would confirm and extend the standard model of cosmology. Some of them died before knowing what it would actually find. And what it found was not confirmation. It found complication. Productive, scientifically rich, intellectually transformative complication. But complication nonetheless. The astronomers now working with James Webb data are not a monolith of crisis. Many of them describe the experience with something closer to exhilaration, the genuine electric feeling of being the first human beings to see something no one has ever seen. That feeling is real, and it coexists, sometimes in the same person, with a quieter anxiety about what the data means for everything they were trained to believe. Science progresses generation by generation, and each generation inherits the models of the one before. The generation that breaks a model carries both the weight of that inheritance and the possibility of being the one that reshapes it. It is a heavy thing to carry. It is also, by any reckoning, an extraordinary privilege. The universe does not care about the careers involved. It simply continues to be what it is, waiting for better instruments to catch it more precisely. James Webb is that instrument, and the people working with its data are, whether they asked for it or not, at the center of one of the most consequential scientific moments in decades. Before James Webb, astronomers knew they needed a different kind of telescope, not deeper, wider. The James Webb Space Telescope looks at extraordinarily small patches of sky with extraordinary sensitivity. Its field of view is a postage stamp. Its findings are transformative precisely because even that postage stamp keeps producing anomalies. Scale up. Survey the whole sky at comparable depth. The anomalies, if they are real, become undeniable. If they are statistical flukes produced by sampling a narrow slice of the universe, that truth becomes undeniable too. Either answer resolves a question currently worth billions of dollars of theoretical labor and decades of scientific debate. The Nancy Grace Roman Space Telescope is being built to provide that answer. Roman, named for the astronomer who was instrumental in creating the Hubble Space Telescope program, is designed with a field of view 100 times larger than James Webb's. Where James Webb sees a postage stamp, Roman will see a poster, and it will see it at sensitivity levels that bring faint, distant galaxies into statistical clarity. Roman's anticipated launch in the late 2020s is not a routine next step in a smooth scientific progression. It is, in the context of everything James Webb has found, a verdict machine. Its primary science program will measure the Hubble constant through multiple entirely independent methods, including weak gravitational lensing, the clustering of galaxies across cosmic time, and the standard candle distances of Type Ia supernovae across a vastly larger sample than previous surveys. If the Hubble tension is a real feature of the universe and not an artifact of limited samples, Roman will make that definitive. Roman will also survey the distribution of galaxy masses and sizes across billions of years of cosmic history. The early galaxy problem, the finding that massive galaxies appear too early and too fully formed in the standard model, is currently based on James Webb's observations of a relatively small number of fields. Roman will observe millions of galaxies across the same redshift ranges. If massive early galaxies are genuinely overabundant compared to Lambda Cold Dark Matter predictions, the statistics will be unambiguous. If they are not, and James Webb was sampling a particularly overdense region of the universe, Roman will reveal that too. Dark energy is Roman's third major target. The behavior of dark energy across cosmic time carries the signature of what it actually is. If dark energy is truly a cosmological constant, a fixed energy density of empty space, its influence should be the same at all epochs. If it is a dynamic field that evolves over time, Roman will detect the evolution through precision measurements of how galaxy clustering and cosmic expansion have changed across billions of years. The telescope is named for a person who spent her career building the infrastructure that made space astronomy possible, often working against institutional resistance. Roman herself argued for broad sky surveys over narrow deep fields, a philosophy now embedded in the telescope bearing her name. James Webb found the questions. Roman is being built to find out how seriously to take them. When it launches, when its first wide-field surveys begin returning data, the distribution of opinion inside cosmology will face a test that individual researchers cannot manage through interpretation alone. The numbers will either hold up at scale or they will not. There is no reading around a survey of hundreds of millions of galaxies. Roman is the next conversation, and it will be a conversation the universe has to participate in directly. Go back to the beginning. Christmas Day, 2021. A rocket rises from a launch facility on the northeastern coast of South America, carrying inside it a mirror made of 18 gold-coated hexagons folded like a flower into a cylinder. The engineers watching from control rooms and parking lots and living rooms across 2 continents had spent, in some cases, the better part of their professional lives, making that moment possible. The rocket performed perfectly. The telescope separated. The unfolding began. No one in the control room that day knew what the telescope would find. They hoped, they modeled, they prepared. But the universe had not consulted the models. And so, 3 years later, we have this. A galaxy producing oxygen in the first 500 million years of existence. Oxygen that requires multiple generations of stellar birth and death to synthesize, oxygen that should not have had time to appear in a universe that young, galaxies with the mass of mature spirals, already fully assembled when the cosmos was less than 5% of its current age. A constant of expansion that measures one value when you look backward in time and a different value when you look at your immediate cosmic neighborhood. A preferred direction in galaxy spin that probability theory says should not exist. Stars that turned out to be entire clusters. Objects whose explanation changed 3 times in 3 years as more data arrived, each revision more startling than the last. Individually, any one of these could be an anomaly, an error bar, a subtlety in the physics waiting to be resolved by better simulations or more careful calibration. The field has absorbed individual anomalies before, but the accumulation sits differently. It is not one discrepancy. It is a dozen discrepancies arising from different instruments, different methodologies, different research teams on different continents, pointing at different phenomena that all converge on the same unresolved question. Is Lambda Cold Dark Matter, the model that has organized and guided cosmology for 30 years, fundamentally incomplete? That question is sitting at the center of the field right now, in 2026, and it does not have an answer, not a consensus one. Alison Kirkpatrick, who in 2022 said she woke up at 3 in the morning, worrying that everything she thought she knew might be wrong, has not stopped working. She is still analyzing the data, still publishing, still contributing to a community that is, in its best moments, collectively honest about the limits of its own knowledge. Caitlin Casey and her collaborators are mapping the early universe's galaxy populations with increasing precision. Stefano Carniani's team is staring at chemical signatures in objects that should not yet have had the time to produce them. Peter van Dokkum, who called one of his discoveries a cosmic miracle, is still looking for more. These are not people in despair. They are people in the precise condition that science most requires, confronted by data that exceeds the reach of current explanation, unable to turn away, unable to pretend the numbers resolve cleanly, unwilling to stop asking. The telescope that produced all of this is still up there, orbiting a gravitational equilibrium point between Earth and the outer solar system, pointing its gold mirror at the oldest light in the observable universe, collecting photons that have traveled billions of light years to reach an instrument that cost $10 billion to build and 25 years to launch. It is sending home data that no one fully understands yet. That is not a failure. That is science at its most alive. The next instruments are already being designed. Roman is being assembled. Ground-based observatories are preparing their own contributions. Future space missions are in proposal stages, funded partly on the basis of what James Webb found, designed to press on the very questions that James Webb opened. The next generation of researchers is entering the field right now, some of them drawn specifically by the anomalies, by the feeling that cosmology is at a threshold, that the next decade of data could reshape the map of everything. The universe is not waiting. It has never waited. For 13.8 billion years, or perhaps longer, it has been what it is, indifferent to the frameworks humans construct to describe it, continuing to evolve and expand and structure itself according to rules that the most powerful instruments ever built are only beginning to read clearly. Science is not the accumulation of answers, it is the refinement of questions. A civilization that can ask better questions is a civilization that understands more, even when the answers are not yet in hand. James Webb Space Telescope has given us the best questions in the history of cosmology, perhaps in the history of our species. The question of how the first light organized itself into structure, the question of what the universe is actually made of, the question of whether the cosmos we live in obeys a principle of uniformity, or whether it has directions, preferences, asymmetries we have barely begun to measure. The question of whether the model that has guided 30 years of science is a foundation or a scaffold. None of those questions are closed. All of them are open, and somewhere in the dark, a gold mirror keeps turning.